So in our last class, we have seen multiple linear regression, right? So multiple linear regression, we have multiple features and one target, right? The equation is actually, having multiple features and one target. You can see the equation of this type, right? These are the equation type. Now, like we have solved a single feature equation y is equal to mx plus b. This also need to be solved. So we have covered this in our last class. So here, if you take only two features out of n features, the equation looks something like this, right? So uh, package is equal to beta naught plus beta 2 into CGPA plus beta 3 into IQ. So here you have two features. You have two features here, right? So in this case, whenever you have two features, this can be plotted in the three-dimensional view, right? This is CGPA and IQ, this package, this is a scatter plot. So like we have seen in the simple linear regression, there it is actually just a line which is approximating those points. But here it is a plane which is actually approximating these points, right? That is what actually we get it from this beta naught, beta 2, and beta 3. So we have seen an equation, and we have to solve the value of beta naught, beta 1, and beta 2. If you consider a generic equation, it will be till beta n xn. And starting from there, we have actually represented the equation with the matrix. And then we got our y cap is equal to x into beta. And we have actually derived the values for beta by using a least square method, ordinary least square method, by finding the error between the actual value of the target and the predicted value of target, which is from that equation, right? And we have minimized the error, and we have minimized the error using differentiating it with respect to beta, and uh, beta value have been found out. Okay, this derivation we have done in our last class. So we have ultimately got our beta, finally beta equal to x transpose x to the inverse and x transpose and y. And what is this x and y value? These are x train and y train values to get the value of beta, right? So now what we'll do is we'll try to take one example to check this. Okay, how to solve the multiple linear regression problem. Okay, so single or simple linear regression we have already seen. With those formula, we have actually found out the value of m and b. In this case, you have to find out the beta matrix, right? Okay, so let us consider, I will just try to use my pen here. Let us consider a data, right? uh, like you have future x1. Okay, you have a feature x1, right? You have feature x1. Okay, and you have feature x2, and then this is the y value. So this is the data given, right? For example, this can be a product 1 sales, and this can be product 2 sales. It can be any data, product 2 sales, and corresponding y value, okay, is something like weekly sales. Okay, weekly sales. right? These are the data. Let us consider this data 1, 4, 1, 2, 5, 6, 3, 8, 8, 4, 2, and 12. So this is actually given to you. These are the data points given to you. Okay, this is an example of multiple linear regression. You have to solve the value multiple linear regression. Okay, so now either we can write something like this equation: beta plus beta 1 x1 plus beta 2 x2, right? So your y cap is equal to beta naught. This is predicted y cap is equal to beta naught plus beta 1 x1 beta 2 x2. So our aim is to find out this beta naught, beta 1 and beta 2, right? So how to find out this beta, right? See, we have seen from our previous derivation that we have actually started from, see, this type of matrix, right? We have started from this type of matrix x beta, right? Like this we have started. Yeah, y naught cap is equal to x into beta, right? So now see, your x matrix in this case, see, we finally got the formula as beta is equal to x transpose x whole inverse x transpose. Okay, now in this x matrix is something like this, which you have seen in our last class. So this is x matrix. Yeah, what you see here is the x matrix. This is your x matrix, right? Right. This is your y matrix. This is your beta matrix. Okay, so we have derived the equation for the beta in this. Okay, now which is x and y in this case? Okay, so let us see this x and y in the example. In the example, what we have seen, x and y, okay, are your x matrix is equal to, okay, your x matrix is equal to, okay, so it is 1, 1, 1, 1. Okay, then you have to put these two, x1 and x2, right? So 1, 2, 3, and 4, 4, 5, 8, 2. Hope you understood this. This is your x matrix. Okay, now you have to get your y matrix. Your y matrix is equal to, is given as 1, 6, 8, and 12. This one. So you got your x matrix and y matrix. Now, what is the formula for beta matrix? Right? Formula for beta matrix we just seen now. What is that? X transpose x whole inverse and x transpose y. Right? So the formula is x transpose x whole inverse, okay, x transpose y. We just have to do this, solve this now. Okay, so it's as usual mathematical, it is just a mathematical simplification. Okay, so let us do this mathematical simplification. So now let us do x transpose x. See, if you have a matrix calculations in the calculator, it will be very easy, right? So your x transpose is 1, 1, 1, 1, right? 1, 2, 3, 4, and 4, 5, 8, 2. 4, 5, 8, 2. This is your x transpose multiplied by x, right? X you know, right? What is that X? The X transpose is actually the one which you have written now. It's very simple, you know that your columns will become rows, right? So that is what I have written here now. Now X is nothing but same thing, that is 1 1 1 1 1 1 1 1 2 3 4 4 5 8 2. Now you multiply this matrix multiplication. All of you know about matrix multiplication, right? Okay, so matrix multiplication, you get it as, okay, you get it as, I have the answer here with me. I'm directly writing this matrix multiplication. What you get here is 4 10 19 10 30. This is what the value I have calculated. I'm just writing it as it is. So you will get the similar value. Method is same matrix multiplication which you do normal multiplication, right? This row, this column, this row, this column, this row, this column, right? Okay. Similarly, next this row, next column. So like that, you can get the values of this matrix. So this is your X transpose X. Now what we require is X transpose X whole inverse, right? So according to the formula, we require X transpose X whole inverse. So what we do here is, for that, take the inverse of this, right? So any matrix inverse multiplication you can use, right? There is one type of matrix inverse method. You take the magnitude of this, right? Residuals of this and divide it by the magnitude, right? You will know about it. Okay, little bit matrix finding inverse, you will have to see if you remember. Okay, otherwise you can use in your calculator. Scientific calculators are having this. You can just use that to get the inverse values. Okay, so inverse values you get is, I'll just write directly here, 3.15 minus 0.59 and minus 0.30. This inverse you got through the same method what I have told you, right? Using residuals and the magnitudes, you can use the same method, or you can use the calculator for that. Okay, so 0.59, you get 0.20, 0.016, right? Minus 0.30, 0.016, 0.054. This is the value which I calculated. So this is what you get as X transpose X whole inverse, right? So this one is X transpose X whole inverse. So now for this you multiply with X transpose, right? You multiply this X transpose, multiply this with the X transpose. That means for this matrix you multiply X transpose. X transpose is same thing again. What is that? 1 1 1 1 1 2 3 4 4 5 8 2. When you multiply this and this, okay, you get another value corresponding to X transpose X whole inverse into X transpose, right? So this is actually coming to be, right? You just have to do matrix multiplication. Okay, so these matrix multiplications are little time consuming. That's why you try to use scientific calculators for this. So I heard that it is possible. Even I have not used scientific calculators for doing this, but I think you can use it, right? But only thing is that you have to find out how to use it, how to get that in the calculator. Okay, so this comes to be 0.05, 0.47, minus 1.02, 0.19, minus 0.32, minus 0.098, 0.155, 0.26, minus 0.065, 0.005, 0.185, minus 0.125 is the value you get. Right? Now still it is not over. Multiply this by y, right? So what is y? Y is given here, right? 16812. Multiply this with the y value. This is 16812, right? So this is going to be your, whatever you get is going to be your x transpose x whole inverse x transpose into y. This is what your beta value is. Okay, so definitely this is 3 into 3, right? This is 3 into 4, and what we multiply 1 into, this is 4 into 1. So what you finally get is 3 into 1 matrix. That is going to be your beta matrix. So that beta value is going to be minus 1.69, 3.48, and minus 0.05. This is going to be your beta matrix. Okay, that means this is going to be your beta naught value. This is going to be your beta 1 value. This is going to be your beta 2 value. Ultimately, your equation will be something like this. Y is equal to beta naught. That is minus 1.69 plus 3.48 x1 plus, now it's minus because this is minus because coefficient is minus, minus 0.05 into x2. This is x1, x2. This is the equation. This is your prediction y. Okay, because you're going to predict y using this formula, and this formula is going to be a plane in the three-dimensional plot of this x1 and x2. This is the way you can find out. Now let us see, we can calculate the values now. For example, now if you take the data, for example, if you take the data, now let us calculate this sales value. Okay, let us predict the sales value for the same data. You can see this is the y value, right? Now what you are going to get is the y cap value, predicted value, right? So predicted value, now y cap, you can predict it from the same formula, which is shown here, right? So you try to fix that value. Y cap is equal to minus 1.69 plus 3.48 x1. What is x1? x1 is going to be 1. Okay, 1 into multiplied by 1. Now then 4 into, sorry, this is minus again, 0.05 into x2, that is into 4. You calculate this value, check how close it to this 1, right? Similarly you substitute x1 is equal to 2, x2 is equal to 5 in the same equation. Try to get the prediction for these values of y, right? So like that you substitute the value of x1, x2 in this, try to predict this, substitute the value x1, x2 in the same formula and try to predict this. So you get another table here for y naught, right? And then using this y and y naught, try to get the error metric. Okay, so how do you get the error metric? I have told you this formula for error metric in my previous class. What is that error metric? Yeah, these are the error metrics, right? You can calculate mean absolute error, by using this formula 1 by n summation y minus y cap mean squared error you can find out. Similarly, you can find out root mean squared error, right? Root mean square error. Similarly, you can find out the R square value, right? So this can be manually calculated just to take your practice on this, right? In examination, you can expect similar problems with the different values in this. You just have to know how to do this, right? So I will give you some questions as an assignment. You try to do this, okay? You practice yourself how to do this. Very simple. It is simple matrix multiplication. That's all, right? Hope it is clear for you, right? It's simple matrix multiplication. Okay, so now the same thing can be done using using Python also. I have an example here. See, one similar example, something related to the electronics, right? See here. Now we can use this multiple linear regression, okay, to predict the power consumption. To predict the power consumption. Now see here, you have been given these independent variables, okay? What are the independent variables given here? Supply voltage, right? Independent variables are supply voltage, okay, and current, load current, operating frequency, temperature, and resistance. So here there are multiple independent variables. So hence it is a problem of multiple linear regression, right? There are multiple features in this. Using these features, you have to predict, right? You have to predict this power consumption. Okay, so now this data set is actually given to you. You have been given this data set, so you will have to find out the the prediction values. Okay, so of course, when such big matrices are given, you cannot depend on a manual computation. Okay, so we have to go for a Python implementation. Okay, so this is actually, if you try to write the equation, a model equation, it looks like this, right? So P is equal to beta naught into voltage, beta 2 into current, beta 3 into frequency, beta 4 into temperature, beta 5 into resistance. Okay, so solving this will be very difficult by manually. So we can just see the Python program for this. Okay, so I have the program here with me. This is the program. Okay, so I'll just simply explain this. It's very simple one. Same thing, whatever you used for linear regression, same thing used. Okay, you have to use pandas, numpy, matplot, and from sklearn we'll try to split our data using data for training and testing. Then we will use linear regression. Then also we will use sklearn for R2 square and mean square error. Okay. First, as usual, load the data. Excel file. There's an Excel file. Okay. So in that Excel file, you have all the data. Okay. So the data is read here. Okay. The data is read. Data is equal to this is the syntax to read the Excel file, and this is the path. Okay, read the data file. Now you just arrange the data for, you give just you just have to give a header for those. Okay, as a first column will be voltage, then next column will be current, next column frequency, then temperature and resistance, and then you have last column is going to be target. Okay, so that is going to be Y. So X is going to be your now training data. Okay, that is the features. Okay, and Y is going to be your target data. This will create a model. This model is equal to linear regression will create a model, and then model dot fit. So here you are going to find out the values of the matrix, right? And then you do the prediction. That is what you calculate y cap using this prediction for the training data and testing data. Whatever data is separated for training testing, you will predict it, right? Okay. So here both training data and testing data is predicted, and from there you can find out the accuracy, the R square, right? So R square is coming to be 0.9053, okay, for the training data, and R square is coming to be 0.9151 for the testing data, right? And root mean square error is going to be 8.824. This model seems to be a better fit, right? Because R square value is coming to be 0.9053, right? So for the both the training data and testing data is quite better than any models, okay? And you can see that what are the values of beta values, okay? You can see here the intercept is minus, this is beta naught, okay? This is your beta 1, this is your beta 2, beta 3, beta 4 and beta 5 values, okay? You can just use a simple model intercept values for this, right? Feature values you can use. This is the syntax to use the feature values. Okay, so you can use a plot it. You can plot it for both actual power and the predicted power. Okay, this is the plot which versus actual power and predicted power. Okay, so almost it is coming to be in line with the actual power. Okay, these are the residuals. So this way you can implement a multiple linear regression with any data. Okay, so this is about multiple linear regression. Now let us do the last part of this linear regression. We have seen in the beginning itself, right? So in the beginning itself we have seen there are three types, right? There are three types, right? There are three types. Okay, we have told that there are three types. That is, one is simple linear regression, multiple linear regression, and the polynomial regression. Okay, so we have seen two out of this. Now we are going to see the third one, which is called as polynomial linear regression. What is polynomial linear regression? Why polynomial linear regression is required? Right. So now this data sometimes, okay, may not be in the linear shape, right? When the data is in the a little bit distributed in the curvical shape, then your straight line and straight plane definitely will not work. In such cases, you have to go for a polynomial linear regression. Okay. In such case, we have to go for polynomial linear regression. Okay. So what is polynomial linear regression? The regression, the model equation, if it is in the form of y is equal to, right, beta naught plus beta 1 into x plus beta 2 into x square plus dash 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 beta n into xn. Okay, this is if your model is in this form, okay, then you can easily predict the values using this polynomial equation. Okay, so what is
I found this on the web for models.
What is polynomial regression? So when there is a nonlinear relationship between the feature and the target, right? In such cases, your linear linear regression, whatever you have used for your simple linear regression and multiple linear regression, may not work, right? So polynomial regression is used when the relationship between input features and the target are nonlinear. Okay, when this relation is nonlinear, your straight line will not fit into that. You need to cut a curved line, right? And that curved line is corresponding to the polynomial equation, right? The curved line is corresponding to the polynomial equation. Okay, so if you see the linear regression, simple linear regression, okay, y is equal to mx plus c, it's also polynomial, but it's of degree 1. Okay, so linear regression in such cases will not work. I told you, right? Straight line cannot capture, but polynomial line can capture it. Okay, so it's a good fit for that particular data set. Okay, the curved line fits data much better. Okay, so curved line can capture nonlinear patterns, it will lower the prediction error, and definitely which will lead to more accurate prediction. Okay, now see here, this is the data you have. When you have the data, the straight line prediction, that is a simple linear prediction, may not work, right? In that case, you have to use polynomial regression. You have to use a line which is the curved one, and the equation for this curved line is nothing but a polynomial. Okay, that is what we are going to see here, right? So now we will see various polynomials here, right? See, logarithmic function. Logarithmic function will give a curved line, right? So this is the rapid rise, then levels off. Now similarly, exponential, e to the power of x. This is slow start, then rapid growth. X cube, you get S shape. Similarly, x square, okay? So quadratic one, you get a shape like this. You get a parabola shape or a bomb shape like this. So this is what the nonlinear relationship talks about. Okay, so polynomial regression. Okay, let us take, like we did actually, ultimately what is required is this beta 1, beta 2, beta 3 values, right? That is what we require, right? So what we do is, so our equation is in the form y is equal to beta naught. This is the intercept actually. So now beta 1 into x, this is the linear term with a degree 1 component. Okay, and this is the linear term. This is with the x. Whatever term with the x square, it is a quadratic of degree 2. Okay, this creates a curve. This creates a curve. Like other powers of this polynomial equation also creates different shapes of your regression curve. Okay, so n is equal to 1 is a straight line, n is equal to 2 is a parabola, n is equal to 3 is a cubic shape. Okay, you get different wavy shape when this n value goes above. Okay, so now we have to learn about these 3 terms in this machine learning. This is very important. What is that? Underfitting, good fit, and overfitting. Okay, what is underfitting? This underfitting occurs when degree is too low. Suppose n is equal to 1. Suppose if you take a data which are non-linear and you try to use simple logic regression to do the prediction. In such cases, what will happen? The model will become too simple, right? So your simple linear regression will just draw a line. In such case, what will happen? It won't actually predict the values, right? So these values will not be predicted using the simple line, right? So what will happen is the model which you got will give high error when you test it with the training data itself, right? When you test it with the training data itself, right? So that's why when you test the same model with your training data itself, if it is giving very high error, then it is underfitting, right? Now, what happens? Good fit. So the good fit is always better. So you use same n is equal to 2 or 3. This model captures underlying trend. Okay. Now it will give low error. Okay. It generalizes the new data. This is the reliable prediction. This is called good fit. There's something called overfitting. What is overfitting? Okay. Overfitting. What is overfitting is it will work better for the training data. Right. So what happens is once you train a model with the trained data, then again you try to predict using the trained data only, it will work well, but it won't work for test data. Okay, it won't work for test data. Any other test data, if you test this some external data, you test the same model, it won't give you good result. That's called as overfitting. Okay, so this occurs when degree is too high. When suppose if the n is too high, this overfitting will work. So this model memorizes the training data only, training will be very good, but test will not work well. Okay, very low training error. Of course, training error will be very less, but test validation error is very high. So this fails in a new unseen data. So what is good is this good fit. So you have to be very careful while using these polynomials. Okay, so whenever you have something overfitting and underfitting, you need to now use something called as regularization, which I will be taking in my in the coming classes. Right, to make a best training, we can use something called as regularization, which we will see later. Okay, so in this slide, I'm just explaining you what is underfitting, okay, good fit, and the overfitting. Okay, now let us see the Python implementation of this polynomial regression. Okay, very simple Python programs are there. Now see here, first you import numpy, import sklearn, and we are going to use import sklearn to create the polynomial features from the data. Okay, and then we use linear regression, same as what we used earlier. Then we use matplotlib. So first you import the data, then create a data. X is equal to np.array. We create a simple data 1, 2, 3, 4, 5, 6. Okay, reshaping it to -1 to +1. Then np.array. This is another data. Okay, why this is the target data? I'm just using. I'm having one. This is I'm just using only one feature here. Okay, so now you make it as a polynomial. Okay, so you have to make it as a polynomial. So this polynomial features will convert this data into a polynomial data, right? So that is what it does. Your data now is going to be, a polynomial data. Similarly, X poly, you just actually convert this data into a polynomial. See, what exactly we are doing with this too is that this X data is converted into a polynomial data. That's all. Okay. So of degree 2, right? So now just you use the same linear regression model, create a linear regression model here. Now then use just model.fit. Okay, I'm just going to use entire value here. I'm not going to use any test train and all. So X poly and Y. Okay, then you just try to get the prediction. So Y prediction is equal to model.predict X poly. I'm using the same training data to get here. Then plot it. See what are you going to get. Okay, it's a simple program. Okay, so first create a data, transform into a polynomial, use linear regression, and then visualize it. Okay, this is what you're going to do. Right? So what does the polynomial do this? Okay, so it's very simple. So what in this program, what we did is you have the input X. Okay, this transformed X poly, what you're going to do is you're just going to make it as 1x, x square, and so on. Then linear regression, use linear regression here, right? Okay, this is what we do here. Original is 1, 2, 3, 4. Okay, this is 1, 1, 1, 1 bias. X linear, it will remain as it is. X square, this is quadratic. Okay, so degree 2. So your data is converted like this into the polynomial. Okay. Now, how do you find out this beta value? It's very simple. We are not going to derive this here. Like we have calculated beta value for others. Here also you can calculate the beta value. Suppose you take, I cannot take till n because let us restrict it to very small matrix. So your equation, your polynomial equation is y is equal to beta naught plus beta 1x plus beta 2x square, right? So you have to calculate this beta naught, beta 1, and beta 2, right? So what is the formula, right? So beta is equal to x inverse beta, right? What is that x and what is that, b, x inverse b. What is that x inverse and b? X is equal to, see, n is the number of degree, right? This is a degree, right? Now, this is the matrix. This is the X matrix. In X matrix, what is n? N, you know, this is that degree, n, right? Now, that's degree of a polynomial. This one is summation xi, right? Summation xi square. Once again, summation xi square, summation xi cube. See, it's very simple to remember. See, these two will come here, and then you append with xi cube. Now these two will come here, append with xi to the power of 4. B is equal to summation yi, summation xi yi, summation xi square yi. These are the formula for x and b. So when you have x and b from the given data, you can calculate the value of beta. Let us take a small example. Right? Let us take a small example here. X and y is given. Right? X and y is given. X is 1, 2, 3, 4. Y is 1, 4, 9, 5. Now using this formula, you have to find out the value of beta. Those are the coefficients of a polynomial equation for polynomial regression. Now, what is required in this? You require this n summation xi square and all, right? So for that, what you do, you make a table. Okay. So xi is going to be 1, 2, 3, 4. 1, 2, 3, 4. Yi 1, 4, 9, 15. Okay. Now, what is xi yi? Because somewhere you need xi yi, right? Xi yi is required. Summation xi yi is required. You make that. Okay. You get xi square of this. Then you get xi square yi. Square of this into yi. Xi cube, xi to the power of 4. Then calculate the sum. Because these are the sums you're going to use in this, right? Then calculate the sum, right? This sum is 10. This sum is 96. This sum is 29. This sum is 96. This sum is 30. This sum is 338. This sum is 100. This sum is 354. Hope all of you understood this. Okay. Now, after this, what you do? Get a beta by you substitute this here. All this, okay. Here n is going to be 4 degree. This is actually, you have degree 4 in this, right? X to the power of 4 is there, right? X to the power of 4 is there. Since x to the power of 4 is there, so it is going to be degree 4, right? The maximum degree is going to be 4 here. Okay. Then 10. What is this 10? This corresponds to summation of xi. What is summation of xi is 10. Okay. Then 10. Then 30. 30 is summation xi square. Summation xi square is here. Xi square is here. Where is this? 30. So substitute all the values here. Okay. Substitute all the values here. Right. Then B matrix. What is B matrix? B matrix is summation of yi. Summation of yi is 29. Okay. You put 29 here. You put 29 here. Right. Similarly, then summation of xi yi. What is summation of xi yi? Summation of xi yi is this 96. You put these values here. Then multiply. You get the inverse of this. Get the inverse of this and try to multiply with the this B matrix. You get this. So this is the value of beta naught. This is the value of beta 1. This is the value of beta 2. So you get the equation here. This is the equation you get. Right? This is what you get, equation. Now this is the model equation. Okay. Now you can get the prediction now? Yes or no? You can get the prediction. Yes or no? Right? Now these are the values. These are the y values. Now for this x value, can you get y cap? Right? You can get y cap, right? You can get y cap. This is actually y cap. Right? This is the prediction equation for polynomial regression. You got this polynomial here. Now you can predict the value of y for the given value of training. Okay, these are the training values. Now for the training value only, you just calculate the value of y, which is going to be y cap. Right? Now you can calculate the y cap here. You can calculate the y cap here. You can calculate it like this. Right? This y cap. Okay. Now for value of x is equal to 1. How can you calculate for this? So y is equal to minus 0.75 plus 0.95 plus 0.75. So what is the value? You can calculate it using simple calculator. This is going to be minus 0.75. Let us calculate this. It is 0.75 minus plus 0.95 plus 0.75. it is coming to be 0.95. This is coming to be 0.95. So what is the actual value? Actual value, the given data is 1 only. So it is almost same, error is less, right? Almost same, this is coming to be 0.95. Similarly, substitute this value. See, substitute this value 2 here. This will be equal to minus 0.75 plus 0.95 into 2 plus 0.75 into 4. See what is the value you get, right? So you can just calculate it as, let us see one more value, minus 0.75 plus this is 0.95 into 2, this is 1.9 plus 0.75 into 4, this is 3. Okay, so this will be equal to 3 plus 1.9 minus 0.75. It is coming to be around 4.15, right? So this is coming to be around 4.15. See how best the model is fitting. See, it's almost near, right? Error will be less, right? So this is the way you can implement polynomial regression, okay, to find the best fit, best curve fit. Here it is actually curve fit, best curve fit for the data you have, right? Okay, so this completes your entire linear regression. Okay, so what we have seen in all the previous slides till today about the linear regression. In that we have seen simple linear regression, and we have seen multiple linear regression, and then we have seen polynomial linear regression. Fine, we have seen these 3 types of linear regression. Okay, you know when this has to be used, when this has to be used, when this has to be used. Depending on the data type you have, you can use this type of linear regressions, and all these are used for the predictions. This is all used for the predictions. If at all you want to do any prediction, then linear regression, either simple, multiple, or polynomial, depending on the data, is the better choice, right? So this gives you how to use the linear regression for your classifications. Okay, so now what is the pros and cons of linear models? Okay, advantage is that it is very simple to use. Right? And it performs well with the data with the linear, which is having linearity. Okay, when the data is most linear, it is okay. Okay, it is not much useful when the data is highly non-linear. In that case, you have to go for neural networks. Okay, and it is highly prone to the underfitting sometimes, and sensitive to the outliers. Suppose if you have outliers, then this may not work, because it will become highly non-linear when you have many outliers, right? These are the pros and cons of your linear models. Okay, so this completes the chapter on linear regression. Now the next topic will be logistic regression. This logistic regression is used whenever you want something to be classified, right? So this linear regression will give you a continuous value, right? But logistic regression is not like that, right? Logistic regression will give you a probabilistic value. That means what is the probability that above this will be high or above this will be low, something like that. Okay, this is basically used for the classification task. Okay, so logistic regression, this is also supervised learning. See, all the things which you have used, which you have learned so far, it's all example of a supervised learning. right? Because we are using a target value for every data, right? So even logistic regression is also a supervised learning. It is used for classification task. Okay, it is used for the classification task, right? So predicting which category an input belongs to, right? Despite having regression in its name, it's primarily used for the classification purpose. Okay, so here what we do here, see, we are going to use the same regression equation only here, but output, right, we use a sigmoid function, right? We use a sigmoid function. That sigmoid function is going to decide, right, whether the output belongs to this class or belongs to the other class. Okay, so instead of predicting a raw number here, logistic regression predicts the probability that an input belongs to a particular class. It does this by taking a linear combination of input features. Of course, it takes the linear combination of input feature itself, right? But instead of giving a continuous raw number output, it will just use a sigmoid function, which maps to a function between 0 to 1. It will map it to the probabilistic function. Okay, and then use that probabilistic function to decide, okay, whether this particular features, okay, belongs to that class or this class. That is what called as logistic regression. How it works? In logistic regression, you have the input. Okay, you have the input are nothing but features, okay, like age, income, test scores, like you have for linear regression. Then take a linear combination. This model computes the weighted sum of the features. For example, you take this, it will compute the weighted sum of the features, and then it will pass it through a sigmoid activation function, right? The result is then passed through sigmoid function to produce probability between 0 and 1. Then you have decision boundary. If probability is greater than 0.5, okay, you predict it to class 1. Otherwise, you predict to the class 0. This is the way the logistic regression is working. Okay, how the training is done. The model learns the best weights by minimizing something called as log loss, or we call it as a binary cross entropy, right? Also called as cost function, using optimization techniques such as gradient descent. See, this whatever model you're getting here, so this one actually will come from, okay, the training, right? And how you do it? By using a training process, okay, called as gradient descent. Okay, it can be stochastic gradient descent. Different types of gradient algorithms are there, and it is going to make use of a binary cross entropy loss. This is the loss function, cost function. Okay, we'll come to that, all those things. What is cost function and all? Cost function is nothing but actually it is an error between the predicted value and the original value of the data. Okay, and that is used actually to adjust the weights of your equation. See, these weights, whatever you see here, na, W1, W2, W3, W4. See, we have to get an optimum weight, these W1, W2, W3, Wn's, so that the loss is the cost function is minimum. Okay, so, and that is possible through this gradient descent algorithms. Okay, so we'll come back to the gradient descent little later. I'm just explaining you what is logistic regression now. So types. How many types of logical regression? Like we have simple linear regression, multiple linear regression, polynomial regression. Here you have binary logistic regression. In binary logistic regression, you have only two classes. Suppose you have a data where you need to classify using only two classes. For example, email. If you want to separate the email as a spam or non-spam email, right? Suppose if you want to classify the data as a disease versus non-disease, right? So in such cases, you have to go for binary logistic regression. Okay. Similarly, when you have more than one class, right? More than one classes. You have classes, different types of cat, different dogs, birds. Okay, suppose if you want to classify the animal as a cat, dog, bird, and different animals, then you go for multinomial logical regression. Multinomial logistic regression. When you have more than two classes, this is what you're going to use, right? Then You have all ordinal logic regression. Right. See, this ordinal logistic regression is used to classify the data into low, medium, high. For example, you have a disease, same disease, right? It can be like, low risk, medium risk, high risk, right? You have the data of a person, say heart rate data, or you have some diabetes data, right? So now you have to classify those data, those patients into these three categories, right? Low, medium, and high. It's all diabetes only, right? But under diabetes, you have low, medium, high. In such cases, you can use ordinal logical, logistic regression. These are the three types of logistic regression you have. Okay. Now, what to do here? So, some of the assumption is that the key relationship between features and the log odds of the outcome is linear. So here, once again, we are going to use the linear equation only. That we assume that your relation is a linear. Okay. Then features are not highly correlated with each other. Okay, which is called a low multicollinearity. That means we see that these features are not highly correlated, which is not same. Okay, feature to feature, there is a difference. Okay. A reasonably large sample size is needed to reliable estimate. That means your training set requires to be very large. Okay. Common uses: email spam detection, disease diagnosis, credit risk assessment, customer churn prediction, sentiment analysis, and all these places you can use logistic regression. Okay. Advantages: it's simple, interpretable, fast to train, output probabilities, work well with the linearly separable data. Limitation: it struggles with a complex non-linear relationship once again. Okay. Sensitive to outliers. Okay. Assumes no severe multicollinearity among features. Okay. See, always we cannot you cannot guarantee the data is highly correlated. So that's, those things are there. In such cases, the next method to this is artificial neural network, which we will see later. Now, logistic regression has this advantages and limitations, right? Okay. So this is actually this is a simple linear regression problem. You have that employee rating and salary hike, right? An organization wants to determine employee salary hike based on their performances. Then you can use this linear regression model. But suppose if it requires, if the organization wants to know whether an employee would get promotion based on the rating, right, or don't get the promotion based on the rating, in such cases linear regression will not work. You have to go for a logistic regression, right? Okay. So you, the same data, same curve which you use here, okay, that is now will be converted into a sigmoid curve, okay, which is having value between 0 to 1. Now you put the threshold, right? Now you put a threshold here. Maybe you can put a threshold as somebody ratings are above the see, you put a threshold somewhere here, okay, say 0.4, right? Somebody above this rating, you promote, okay, and somebody below this you don't promote. This is called as logistic regression. Okay. If you want something like this from this, okay, you need to have this particular curve, not the one which you get it from the linear regression. Okay. Linear regression will get the value, it will get a salary hike only, right? Now here you have only two possibilities, promoted and not promoted, something like that. Okay. So based on the threshold value, the organization can decide whether an employee will get salary increase or not. Okay. So let us understand this now, logistic regression, right? So see, now this logistic regression, whatever we use is something called as odds of success. Okay, what is the odds of success? So odds of success is written by odds of theta. Okay, odds of theta, which is actually the ratio of probability of an event happening divided by probability of an event not happening, right? Suppose if you take probability of an event happening as P, probability of not happening event is going to be 1 minus p. That's all called as odds of theta. Okay. What is that odds? Which is nothing but odds of success. Now, consider a straight line equation. Consider this equation, which is y is equal to beta naught plus beta 1x. This is actually coming from your simple linear regression. So y is equal to beta naught plus beta 1 into x. Okay. Now, what is the odds of theta for this? Okay. So if you take a logarithm of this, right? If you take a logarithm of this probability, okay, that is going to be log of p of x divided by 1 minus p of x. Okay, log of this odds of success, that is actually is equal to this beta naught plus beta 1 into x. Right? So now this value, whatever you get, we are trying to convert it into the sigmoid function, right? That's why we are taking the log of this. Ultimately, while solving all these things, we will get a sigmoid function only. That we will see, right? So take a log of this. Now let us solve this. So see what exactly we are doing. We are trying to convert this line to a sigmoid, right? Which is the S line. So how do you do that? So now that's what we do by using the probability, right? So now solving this. Let us solving this, right? Okay, take log exponential both sides. See, solving this equation is only through taking exponential. Okay, exponential of ln of this is equal to exponential of this one, right? This is just taking exponential. Okay, now then do the solution. Okay, so this can be solved like this. See, exponential of ln of x is equal to x only. So same thing. So that will come here. This will be e to the power of beta naught plus beta 1x. Okay. Let us consider this as a y, just for simplification. Okay. So let us consider this y is equal to e to the power of beta naught plus plus beta 1 into x. Just solution. Okay. So then we can write. Okay, this equation as p of x into multiplies. Okay, y into 1 minus p of x. Okay, simplify for y. Okay, so y you will get it as this. Then simplify p of x. Find the probability p of x. So p of x is coming as y divided by 1 plus y. What is y? Y is this one. We are taking this as a y, right? Sorry, not this one. We are taking this as a y. Okay, replacing this as a y for the simplification, right? So now what we get is p of x, 1 minus p of x is equal to y. Simplify for y, simplify for p of x. Simplifying for p of x, you get this, right? You get this. Okay, now you can still simplify this. Okay, divided by e to the power of beta naught x divided by e to the power of beta naught x plus beta 1x, right? So you divide it by e to the power of beta naught plus beta 1x. This also divided by e to the power of beta naught plus e to the power of plus beta 1 of x. What happens? So this will get cancelled. It will become 1. Now if you take a common, this will get cancelled. What will remain is e to the power of minus beta naught plus beta 1 into x. This is what you get, right? Simplifying this, you get this. Now see how you get the probability as how you get p of x as a sigmoid function. This is your sigmoid function. Right? So how we started from here, right? And how we reached here to the sigmoid function. This sigmoid function is the base for your logistic regression. Okay. So let us take one example. I think after this example, we will finish our class. I think it will be too much if I take more class now. Okay. Now see here. It's very simple. You can understand in a very simple way. Simple probabilistic this thing is this. problem. Given this data, okay, just try to understand the steps in this. Very simple. This is numbers of hours of study, right? See here, it says that if 29 hours of study, that he will fail, 15 hours he will fail, 33 he will pass, 28 he will fail. This is the data given. Now, what you have to do, calculate the probability of pass for the students who studies 33 hours. You have to get that P of X here, right? Okay. So then at least how many hours student should study that makes he will pass the course with the probability more than 95%. Here probability is given, reverse you have to calculate. How many hours he has to calculate? Two things you have to do. Okay. Now here one thing is given. Okay. Your log of odds is given as minus 64 plus 2 times into hours. You know that beta naught plus beta 1 into x, right? This is given. This beta naught and beta 1 is given to you. Okay, now you have to solve the problem. Okay, so how do you solve the problem? Okay, now sigmoid function, right? You have to use the sigmoid function. You have to calculate the probability, I said, right? So probability is given by this, you know that, right? So probability P of X is given as 1 divided by 1 plus e to the power of minus z, right? I'm taking it as a z here, this value. So that z value is equal to this one, yes or no, right? This is beta naught plus beta 1 into x. The same thing we got it here. Hope you remember this in my previous derivation, right? We have to find out that P of X, the probability you have to find out now, right? Okay, now just substitute this z here, just substitute z here. You get the probability, right? See, it is given here. See, it's given here for 33 hours. What is the probability, right? So just put the hours is a 33. Then calculate the value P. So probability is now 0.88. Now 88% that he will pass, right? If he studies 33 hours, okay. If he studies 33 hours, okay, the probability is 0.88 that he will pass. This is what actually you have to calculate as a probability for that particular data. Let us now tackle the next question. At least how many hours student should study that will make he will pass the course with the probability 95%. This is a reverse problem. Okay, it's a reverse problem now, right? Okay, first one we got that there is 88% chance that he will pass. Now let us the next version of this is the reverse of this. Okay, reverse of this. You just have to put the value of P as a 0.95 and z is given there. Just solve this equation. Just solve this equation. That's all, right? Just solve this equation. This is another example. This is another example. Now in this, I'm just leaving this the other part to you, right? Now other part here, what you do is this very simple one. I will tell you. This 0.5. It is given as 0.5, right? It's given as 0.5, right? Now is equal to 1 divided by 1 plus e to the power of minus 64 plus 2 into hours, right? 2 into hours. Now in this equation, solve for hours. Solve for hours. That will tell you that to get a 95% of passing probability, how much hours he has to study. So he will get that hours value here. Okay, this I will leave it to you to calculate the hours. So how many hours he has to study to get a probability of 90% of passing. That's what actually answer for the second question, this one. At least how many hours the student should study that makes him pass the course with a probability more than 95%. Just reverse calculation. Here in this, just substitute the value of P is equal to 0.95. Here there is only one unknown, right? So you can just solve this, right? Okay. So 0.95 plus 0.95 into e to the power of minus 64. We take the logarithms and you can just solve this. Just solve this. I will leave it to you. This simple mathematics. I will leave it to you. Okay. Now similarly, we have another example, something like this. Okay, customer income. This is the customer number. This is the customer number, income, and lot size. Okay. So this I will do it in the next session of in the class. Okay. So till now we have done logistic regression. Logistic regression is actually used to do the classification, right? But linear regression is for the prediction. Always you have to think about it. Okay. Remember that. Okay. So here we use that sigmoid function to do the classification into different classes. Okay. So next problem we will just try to solve it in the class. Okay. I think today it's enough, right?